Hello, I'm Rolando.
Hi, I'm Sydney,
And I'm Valerie.
and this is our physics project. And we chose to do the experiment with the ball, where we have to find the electric potential and the electric field both inside and outside of the ball, with the given charge density of rho sub 0 times r over the greater R. And here is our graph for the charge density of the equation of the ball. At the ball's center, where r equals 0, rho also equals 0, meaning that there's no charge at the very center of the ball. But as we move radially outward from the center of the ball, the charge density increases linearly, which is proportional to the radius, until the point where r equals greater r, when these two variables equal. So here we've reached the ball's maximum charge density, which is rho sub 0.
Now, what if we wanted to find the electric field at every point in and around the ball? A derivation of Coulomb's law shows us how to find the electric field using integration. And while we could solve this 3D integral, there's an easier way. One of the most important features of this problem is its spherical symmetry. Because the charge density depends only on the radius, this tells us the electric field must also be spherically symmetric. In fact, the electric field must point radially outward, and its magnitude is solely dependent on the distance from the center of the sphere, little r. In physics, we can often exploit symmetries to solve problems like these. Instead of solving this complex integral, we can use a much simpler yet incredibly powerful tool to find the electric field at every point, Gauss's law, which says that the electric flux is equal to the total enclosed charge divided by epsilon naught, the permittivity of free space. Okay. To find the electric field everywhere, we must break the problem into two parts: the area inside the sphere, where little r is less than big R, and the area outside the sphere, where little r is greater than big R. Let's take a look at the field outside the sphere. We can choose a spherical Gaussian surface such that its radius r, little r, is greater than the radius of the ball, big R. Thanks to the ball's spherical symmetry, the electric field is everywhere normal to the surface. So the left side of the Gauss's law equation is simply the electric field, or the magnitude of it, times the surface area of the sphere A, where the surface area is equal to 4 pi r squared. Our surface encloses the entire ball, so the enclosed charge will be equal to the total charge of the ball. Integration of the charge density function over the whole volume of the ball allows us to find its total charge. We did this using integral solving software. With all the necessary pieces required to use Gauss's law, we can quickly rearrange the equation to find that the electric field is rho naught times big R cubed divided by 4 times little r squared times epsilon naught. What about the electric field inside the ball? Let's find it by shrinking our Gaussian surface such that its radius little r is smaller than the ball's radius big R. Once again, the left side of the Gauss's law equation is simply the electric field times the surface area of the surface. The key difference is that this time our surface does not enclose the entire ball, so the enclosed charge will be less than the total charge of the ball. How do we get around this? We compute the integral of the same charge density function as before, only this time we choose our bounds of integration to be 0 to little r. In other words, we only integrate over the volume of the Gaussian surface, not the volume of the entire ball. With all the necessary pieces required to use Gauss's law, we can quickly rearrange the equation to find that the electric field is rho naught times little r divided by 4 times epsilon naught.
Okay, now we'll find the electric potential at every point in space, and we're going to use a derivation of the electric potential energy equation, which is the electric potential equals the change in potential energy over the test charge, which can be derived to the integral of, or the negative integral of the electric field towards a path of your choice. And so we can do the same thing as we did for the electric field, where we calculate the potential from little r is greater than big R, and then also for little r is less than big R. And so for little r is greater than big R, we were able to find that the electric potential is negative rho of sub naught big R cubed over 4 epsilon naught times negative 1 over little r plus 1 over big R. And then our electric potential for little r is less than big R is the electric potential equals negative rho sub naught over 4 epsilon naught times big R squared over 2. And so those are electric potentials at the different ranges of R values.
Let's plot the electric field against our variable, little r, to see why this solution makes sense. At the center of the ball, the field starts at 0 and increases as we move toward the surface, where little r equals big R, and its magnitude reaches its maximum. Past the surface, the graph of the electric field drops off, approaching but never quite equaling 0. When calculating the electric field of a charged ball at a point very far away, when little r is much larger than big R, the magnitude of the electric field is very small, and the field behaves similarly to that of a point charge. This means that the effect of the non-uniform distribution of the charge on the electric field is negligible from far away.
We can sense make the electric potential now of based on our equations, and we can see that the numbers didn't quite work out how we wanted them to work out. We know that the electric potential should be the negative integral of the electric field, but when we tried to graph the electric potential, it didn't quite look like what it should have looked like. This could be because of something that happened in our integral of where we set the bounds. Maybe we made a mistake somewhere there, but we're going to use another method of sense making to figure out if our solutions still make sense.
Okay. And guess what? They make sense. So for the electric fields, we had rho as coulomb per meter cubed times R, which is just meters, all over epsilon naught, which was coulomb squared per Newton meter squared. And those both equaled newtons per coulomb. Yay! And for potential, it was a little bit funky, but for rho, we had coulomb per meter cubed over coulomb squared per Newton meter squared. All of that times meter squared, which ended up equaling Newton meters per coulomb. And the last one was very similar.
We've been building up to solving problems like these ever since week 1, lecture 1, when we went over point charges and how to calculate the electric field created by them. Even though this is a sphere, we see that its behavior, the behavior of the electric field, does resemble that of a point charge as little r, approaches infinity. We've also seen a problem very similar to this one in Studio 3, Activity 3-4, when we calculated the electric field of a uniformly charged sphere. The challenge was that this time around, the charge distribution of the ball was not uniform, so we required a volume integral to find the total charge of the ball.
Okay. Another problem where we did electric potential solving was during week 4, I think, lectures, where we were finding electric fields from potential and potential from electric field. So determining the relationship between those two. And yeah, that's everything. Thanks.
Or even this wave. Like
Yeah. Oh yeah, the awkward wave. Okay, nice. Okay.